Hello, friends. There's an injustice that is just gnawing at my soul right now. I feel haunted. You see, Charles Augustin de Coulomb deserved better. Everyone treats him like a second-rate scientist, as though his big claim to fame was knocking off Newton's ideas. And it simply isn't true. If you do a simple Google search for Coulomb meme, it's just image after image comparing, oh, Coulomb's law looks just like the law of universal gravitation. He's a knockoff artist. He's a biter. And it just simply isn't the case. If anything, it says more to do with, oh, both quantities radiate out through space. No one talks about brightness dropping by the inverse square law and says that candles ripped off gravity. Charles Augustin de Coulomb lived in France in the late 1700s, and he's so much more than he gets credit for. All right. So, first of all, he was in the French army and held the rank of lieutenant as an army engineer. When it comes to geotechnical engineering, his work on the retaining wall was revolutionary. Uh, Pardon the French joke there. He was one of the pioneering scientists in the study of friction. Field, like we have mechanics, we have electrostatics. Well, tribology, the study of friction, he was a major contributor to that. And also to our understanding of angular motion, where you have what's called torsion, the effects of torque. Well, he studied that extensively. And that actually is what set him up to be able to design an experiment that could verify any sort of quantifiable amount of force between charges. I mean, who hasn't seen two charges attract each other? I know I have. Let me tell you a story, kids. 2006 or 7, I'm walking around the campus at USF, heading to class, and I see somebody who's also walking to class, and they're wearing what was at the time the standard issue BDs for every single student at USF. It seemed like everyone on campus had the same green USF hoodie. But what was remarkable about this student's hoodie is that there was a thong stuck to the back of it. I imagine that they had just gotten it out of the dryer, where a very dry environment with no water to like offload charges to discharge onto, well, you'd have a buildup of charge. And as the nylon fibers, I'm guessing, I didn't go up and pluck one off and take it to the chem lab, in the undies and the cotton of the hoodie rubbing against each other, charge separation due to friction, you're building up a voltage, a difference between the two objects in charge. And nylon is a really good electron acceptor. Cotton's a really good electron donor. They build up a big difference in charge. And that's enough attraction to hold that pair of undies onto that hoodie the entire way to class. It's like, what do you say? Do you stop them? Hey, you've got panties on the back of your hoodie. Well, then you look like a creep. I don't know why, but I feel like you would. Like, it's just not a good look. But then again, neither is having underwear on your back. Am I a bad person for letting that rock? Like I said, I'm a haunted man. But getting back to Coulomb, he advanced the study of electric force by not just acknowledging it, but giving us the first steps to quantify it. And then, not only that, he found the proportions and then did the same thing with magnetic poles, not just electric charges. He's much more than not Newton or the French Newton. He was an interesting man in his own right, and one that deserves more respect than he gets, I think. So let's now investigate his work, take what we can from it, and give credit where it's due. Electric force is a field force. That means that two charges don't have to be touching in order for there to be a force exerted. That would be a contact force. Field forces are able to act over distance. And every field force I can think of dominated by the inverse square law. Anyway, of attraction and repulsion. So it can be attractive like me or repulsive like your mama. And that acts between objects that have electric charge. It's often written as net electric charge or unbalanced electric charges, but that's simply not true. Consider that the electric force is much stronger than is gravitational force. Why then is it not the one that holds together galaxies, solar systems, planets and their moons? Why is electric force, which is much, much, much stronger than gravity, not the dominant force in creating the large scale superstructures of the universe? What a lot of misguided people will tell you is that it has to do with the distance. Well, gravity can act over an infinite distance. Yeah, well, so can electric charge. It's a universal inverse square law, too. It could act over the distance from the Earth to the moon, no problem. Why then is it not the winner? Well, because stable matter tends to be electrically neutral. This was one of the big take-home points in your chemistry education, was that matter tends to be most stable upon becoming electrically neutral. It's often given as an anthropomorphized kind of, it wants to have a full outer shell of electrons, or it wants to form bonds to become stable. It's not a want, it's just the stable state is the one that can last. All the unstable states will therefore be relatively temporary and end in a stability. So if the moon is electrically neutral and the Earth is electrically neutral, does that mean there is no electric force? No. Every proton in the Earth pulls on every electron in the moon. But every proton in the moon, since it is electrically neutral, is accompanied by an oppositely charged particle. So if all of our protons pull on all the moon's electrons, they also repel all the moon's protons. There's attraction and repulsion of equal magnitude. Thus, they cancel out. But canceling out is not the same thing as not existing. I digress. Before they let you out of middle school. Now, I realize they let a lot of kids out of middle school these days without even the ability to read. I'm looking at you, Turkey Creek. But you should have been able to fill out this little chart. That if you take a positive charge and a positive charge and place them next to each other, the electric force between them will be repulsive. If you take a negative charge and a negative charge and place them next to each other, the electric charge between them will be repulsive. And if you take a positive charge and a negative charge, the electric force between them will be attractive. This would have all been relatively common knowledge by the time of Coulomb's later work. There's some overlap of like formalizing this. Like it was during a, a Coulomb's lifetime where there was discovered to be two types of electrical fluid, positive and negative. But he would have been aware of this. And I did mention a moment ago that his big claim to fame before this was his study on torsion. So he had done these studies of metal wires. So imagine suspended from a metal wire a glass rod. On either end of the glass rod, a metal sphere identical in material, size, and shape. This was important to him. He was not terribly certain about how transfer of charge worked, other than you touch two things, charge is transferred. But he figured, and was completely right about this, if you have two identical objects in material, size, shape, blah, and one of them is charged, so we're going to need to add a third one in. If they are brought together and made to smooch so that there is a spark between them, electrons transfer. Not that he would have known anything about electrons at the time. Electric fluid is transferred, but you and I know it's electrons. And since they were identical, there's no property that should favor one over the other, meaning it should be an equitable split. He was right about this. So let's say that this one started out with a charge positive Q. Then when they touch, if this one was neutral, the law of conservation of charge tells us that the total charge before is equal to the total charge after, 0 plus Q, and then each one is going to have equal charge after, so it must be half of Q went to each. So this guy has a charge of Q cut in half, and this guy has a charge of Q cut in half as well. Or as QE as I could make that look. Now, what are these two things going to do to each other now? They will repel. And he had spent some serious time measuring forces, well, I guess torques, on a torsion rod set up like this. So he was able to start quantifying it. And he found by touching this one to this one, it cuts it in half. But then if he spun it around and touched it to this one, Q cut in half, split evenly, would give you Q over 4 and Q over 4. Keep touching, Q over 8, over 16, da, 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 da. You could keep going and cutting it in half every time. Now, he had to use these relative amounts because there was no way to measure an absolute amount of charge. He did not know what the original charge Q was, but he did know that it got cut in half. He could describe it proportionally, but not absolutely. But he found that the force was directly proportional with the magnitudes of the charge. So when you had the two that were halves, because both of these were cut in half, half times half is a fourth. Direct proportion. One side got half and half, this side got half times half as well. Same thing happened on both sides, direct proportion. But also, as these repelled, he was able to measure that the torque dropped. And it dropped by the inverse square of the distance. So he was able to confidently state that electric force was proportional to the quantity of electric fluid on object 1 times the quantity of electric fluid on object 2 divided by their separation squared. Sure, it looks like Newton's law of universal gravitation. That tells you that the universe just isn't very creative, and it just copied and pasted the same thing 4 times. Not that somebody doing their best to describe it as they see it should be considered at fault for that. Make a note of the proportions involved, that this is direct, and down here we have a good old-fashioned inverse square proportion. The inverse square proportion pops up for literally every radiated quantity. Brightness coming from a candle, um, beta particles coming from a radioactive waste dump. Anything that spreads out over space is going to become more dilute as it spreads out. It's right there in the name, spreads. It becomes more dilute with distance by the square of the separation. Let's take that candle as an example. If you have a candle and you hold in front of it a card with a square cut out of it, not too terribly dissimilar from stuff we'll be talking about later when we get to light. But if we have a projector screen over here, if the projector screen is d distance away from the candle, you get a projection that is d tall by d wide, meaning the brightness or the intensity of light coming out of the candle gets distributed over the square of the distance. And if you were to do it 2d away, 2d squared must have 1/4 the brightness. Works with gravity, works with radiation exposure, works with magnets, works with electric force. Don't get hung up on trying to call Coulomb a biter. Now notice that this is simply a proportion, and this was as far as he would have been able to get with it at his time because there had not yet been a device that could measure it as an absolute amount. Strangely enough, it was his torsion rod that would be kind of rebuilt as an electroscope that would allow for the magnitude of charge to begin being measured. And in what units would it be measured? Well, not only did Coulomb help figure out the relations involved in electric force, he was one of the guys that the revolutionary government called up to help devise what became the metric system. And you guys know how I feel about the metric system. So for a primitive electroscope might just have the leaves, but one that was more like Coulomb's design here would have a hinge with a little bar. If this was negative, it would scare all the negatives down to this side. Then this would repel here because this side is all positives because it gets polarized. So everything low would be negative. It would repel, and this would angle up to a certain angle above or below, depending on whether you had attraction or repulsion, whatever. And from the angle, you could begin creating quantified measurements, at least of the charge that was on here. This is just a proportion, though. If you want to use this with such certainty that you feel comfortable putting an equal sign there, then you need a constant of proportionality, similar to the big G constant for gravity. There is a constant here. Coulomb's constant has a lot to do with how well space lets electric force travel through it, what's called uh, permeability. But that is maybe above our pay grade for right now, and we'll come back to it another day. But Coulomb's constant is given the symbol lowercase k, which is often the case for these constants of proportionality. You saw that in friction, you saw that here. If you looked at old ways of writing most proportions, k is given as the, or kappa would be used as the constant of proportionality. And it is worth 9 times 10 to the 9th power Newton meters squared per square Coulomb. It's easy to remember the units because force is in newtons, so that would need to be on the top. You need square coulombs on the bottom to cancel out these coulombs, and you'd need square meters on the top to cancel out the distance squared. Some people use R for this. I'm sure that there's some weirdo out there who uses S for separation. I kind of flip-flop back and forth between using R and D for this. So when we introduce that, we can rewrite Coulomb's law with an equal sign. Coulomb's constant times Q1 times Q2 divided by the separating distance squared, where Q is quantity of charge measured in coulombs. D is the separating distance in meters. K is given right here. And F is to pay respects in newtons. We spent a lot of time talking about different gases in our last unit. One of the most interesting gases in the universe is helium. Helium is notably different from hydrogen for having twice as many protons, 2 to hydrogen's 1. But how could it possibly have more than one proton when protons repel each other? Shouldn't anything with more than one proton just blow itself apart? Well, stay in the class. There are other forces to talk about. There must be something stronger than repulsion, with enough force to hold the nucleus together. A strong nuclear force. But a force for another day. Charge 1 is a proton. One proton carries one elementary charge worth of charge, which is 1.6 times 10 to the negative 19 coulombs, but it's positive. Q2 would be the exact same thing. All protons in the universe are identical. Why are they all identical? That's actually a really good question. There's a Nobel Prize in it for you if you can figure that one out. One of the most compelling theories I ever heard about that was that the universe has exactly one proton in it, and it just weaves in and out of space, kind of above and below. So everywhere you see a proton, it's actually just the one but it's like the same thread coming through a sheet of fabric at different points because it's crossing from above and below. Wild stuff. There's everything that we have been given. Some of it you might have had to spend some time with your equation sheet to look up, but that's okay. That's good character building stuff for you to do. And if you don't like it, for Q and Q2, force would be equal to 9 times 10 to the 9 Newton meters squared per square Coulomb, 1.6 times 10 to the negative 19 coulombs. I could write that again, but I'm not going to. Anytime you have the same number by itself, why type it or write it twice? Although I can already see that the square coulombs will cancel. Divided by something else that's going to be squared. 2 times 10 to the negative 15 meters. You need to decide for yourself whether you prefer to do your powers of 10 on paper or simply type it into your calculator exactly as is. I usually do the first couple ones in my honors classes on paper, just to help them not have to do so much scientific notation. What's 10 times 10? Of course, it's 100. That's 10 to the 2. What is 100 times 100? 10,000. That's 10 to the 4. So 10 to the 2 times 10 to the 2 is 10 to the 4. 10 to the 2 squared is 10 to the 4. So what would 10 to the negative 19 be squared? 10 to the negative 38. 10 to the negative 38 and times 10 to the negative 9 should be 10 to the negative 29 over 10 to the negative 30? I don't know. Let's just get a calculator out. And now we play the most dangerous game where I put my phone on the document camera. 9 times 10 to the 9 times 1.6 times 10 to the negative 19 squared. Oh, apparently I lost a power of 10 when I was doing it in my head. Oh, no, it moved it because of the numbers. That makes sense. Okay, I am still good at math. Dad can still be proud of me. 2 times 10 to the negative 15 squared, closed. Wow. That actually worked out to be a really nice round number, didn't it? 57.6 newtons. Before I turn the page and move on, I do want to point out that we got a positive answer. And what would 2 protons do? They would repel. Anytime when you plug in to Coulomb's law, if you get a positive answer, it means that there is repulsion at work. And anytime that you get a negative answer, you should be getting attraction. Or you can think about it like this. Positive times positive, positive answer. Positive and a positive repel. Negative times negative, positive answer. Negative and negative repel. Positive times negative, negative answer. Positive and negative attract. All right. Earlier I mentioned that the Earth and the Moon are held together by gravity. Well, how much mass involved is there in this case? This would be a lot of stuff that we're going to need to look up, but I feel like this one might be worth it. If I remember correctly, for the Earth, it's 5 point number over 5 times 10 to the 27 kilograms. Mass of Earth, 5 point 9, 7 times 10 to the 24. I must have been thinking of Jupiter. Mass of the moon. And we need the Earth, moon, distance in civilized units. Of course, kilometers are not going to be terribly useful for us with our gravity equation or our electric force equation, but that's okay. Kilo just means stick 3 zeros onto the end of it to get it to be the base unit. More stuff that we would need for this: the elementary charge, which will, I guess, serve to build up to our quantity of charge. And that is 1.6 times 10 to the negative 19 coulombs. We'll also need Coulomb's constant and big G. 6.67 times 10 to the negative 11 Newton meters squared per square kilogram. It has been a while since I've had to use big G. Let me double check on that. Gravitational constant. Why would I ever doubt myself? Of course I had it. We would start by first finding the gravitational attraction. Then we match that to the electrical attraction. And then, once we have the Q, the buildup of charge would be equal to the number of elementary particles, in this case, electrons, that have to be moved, times what one electron is worth. That's the Coulomb thing. So since these two forces need to be matched, we should be able to sub one in for the other. And when we write this, the charge of the Earth, now electrons are moving from Earth to the moon. If the Earth is losing electrons, the Earth must be positive. But charge is conserved. If the Earth starts out neutral and loses electrons to become positive, if the moon is picking those up, it should become negative by the same amount that the Earth becomes positive. So I think that it could reasonably be written as a single charge that is appearing twice. Now you're thinking, well, one of them's positive, one of them's negative. Look, we already know it's attractive, right? Agreed. This is also attractive. Everything in this problem is going to be attractive. It's one of those things like where you have everything in a kinematic problem going downward. So you just decide, even though it's unconventional, even though it's a little bit freaky, I'm going to write down as positive because I'm so bad. I play fast and loose with all the rules. I wear a leather jacket and comb my hair with a switchblade comb because I'm a bad dude. Well, it's one of those situations. I'm just not going to worry about it. I know that these are in the same direction. I'll leave signs for another day. But now I've arrived at something. The distance canceled out. I didn't even need to look that up. Not regretting the choice to spend time looking that up at all. Sweet. Moving some stuff to the other side. GM1, M2 divided by K square root should be equal to the quantity of charge we want, which should be equal to NE, and N is the ultimate answer we want. Thus, we should be able to one-shot this 360 no scope on our calculator with this. That's going to be a lot of typing, but it's, I suppose, doable. this point, now that we've derived an expression for the number of electrons that need to be moved, we will plug in all of the stuff that we have here. Anytime something is in scientific notation, please put the entire term in a set of parentheses. It's just good practice. It helps prevent your calculator from getting the order of operations wrong from your intentions. And by the way, I'm very confident in this expression because it was relatively simple to set up. And n should be unitless. Therefore, I have pre-canceled out my units. I know I'm normally very good at writing them. This time I'm going to do what you guys do and not write them, but I'm justified in doing so, unlike you guys. And E, the charge of a single electron, is 1.6 times 10 to the negative 19. And now it is calculator time. And is it ever? Again, the most dangerous game. Square root of 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24, not 27. That would be Jupiter. Times 7.35 times 10 to the 22. That's the entire numerator. But now we must divide by k, which is 9 times 10 to the 9th power. Close it. Close it. One more close. Divided by the elementary charge, which is 1.6 times 10 to the negative 19. There we go. So to get the Earth and the Moon to be twice as pulled together by manipulating the count of particles on each, 3.56 times 10 to the 32 electrons would need to be moved from the Earth to the Moon. 3, 5, 6, 4, 1, 2, 1, 6, 1, 6. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Which sounds like an awful lot of electrons, doesn't it? But then again, there's a lot of mass in the Earth and the Moon. I almost feel like it would be nice to compare them based on like equal footing. So let's figure out what the mass of that many electrons is. The mass of a single electron is always the same, just like the charge of a single electron is always the same. Again, no bell in the wings for anyone who figures that mystery out. But the mass of electron is about 9.1 times 10 to the negative 31 kilos. So if we multiply that number by how much mass one is packing, 9.1 times 10 to the negative 31. Okay. 324 kilos. 324 kilos. That's like 3 guys. Like, that's how much material you would need to move. That's how much material you would need to move to create the exact same amount of force that the combined masses, now look at those masses compared to 324, but to match the magnitude of that force. two complete worlds, both large enough to crush themselves with their own gravity. There's just three dudes worth of matter. Do you see what I mean now when I was saying like gravity is really weak compared to the electric force? Anytime you do a comparison of them on like any sort of equal footing, you always end up with these astonishing results. Of course, the simplest one that I can think of is you could just rub a couple of electrons off of a pair or off of a hoodie onto a pair of panties, and then a couple electrons would win a tug of war with the electric force compared to the combined mass of the entire planet beneath them pulling them down. Right? To lift something, you've got to hold it with at least as much force as its weight. And the electric force was able to do that by just moving a dozen or two electrons from one object to the next. Consider that next time you see something hanging or stuck with the electric force. There are some true weirdos out there who write stuff like this. Earth's surface gravity is 9.81 newtons per kilogram. This strange notation is driving home a different point than this equally true statement here. Earth's surface gravity does create 9.8 newtons of force for every kilogram of mass at the Earth's surface. But it also makes any object that is falling accelerate such that it gains 9.81 meters per second of speed for every second it spends falling. Both of these things are correct. It's just they emphasize different effects of Earth's surface gravity. This, the creation of weight. This, the causing of falling and the acceleration due to the surface gravity. But both of these are completely valid ways of thinking about it, as long as we're talking about the Earth's surface gravity. Now, usually, we favor this notation. But I would argue that this starts to become more important if you are talking about not just sea level Earth's surface, but if you talk about somebody digging deep into the Earth, well, their weight should do what if they get closer to the center of the Earth? You're right, it would increase. And if they were on top of Mauna Kea or Everest, they'd be very far away from the center of the Earth. And presumably, if you had an incredibly precise scale, you might notice that their weight has dropped by that inverse square law. If we're going to change the distance, then this notation, as long as we aren't changing the object, but we're changing the distance, I like this notation. Think about it like this. Let's say you were trying to find the weight of an object as a result of gravity. So the force of weight is the force of gravity between two objects. Now you're often tempted to just move that m to the other side so that it cancels stuff out, get g. But if you do that, you get this for a brief moment before it cancels. Newtons per kilogram. If we were going to change that distance, I would argue this is incredibly useful. We already see this with Coulomb's law, where you have a given charge, you're moving it around, And historically, that was all they could do. They had a given charge. You didn't know how much you were given because there was no unit or way of measuring that yet, but you could control the distance. So to do the same thing with Coulomb's law, it would be kind of like this. Newtons per Coulomb. Okay. And then at a given distance and a given charge, you would have the amount of newtons per Coulomb. You stick 2 coulombs there, you'd know how many newtons of force are going to act on it at that spot near that charge. You see how this is kind of like if you dig into the earth 1 mile deep, having a ratio of newtons to kilograms would allow you to predict the weight of any object you stuck there at that distance. Newtons to coulombs allows you to predict the force that any charged object would experience at a certain spot around a certain charge. So this would be gravitational field potential. What would it potentially be if I stuck an object this far from the Earth? This would be electric field potential. And again, all it does is allow you to kind of predict generally what's going to be the case. All right, so we got a charged up sphere, and we want to find the electric field potential it has at a distance of 50 centimeters. All right, relatively easy. Our electric field potential is our unknown. The charge of the sphere is negative 15 nanocoulombs. Our separating distance is 50 centimeters. Notice we've got 3 sig figs here, so we can get 3 sig figs if both of those have 3 sig figs, and that's what we can have our answer round to. But nano means what? Centi, milli, micro, nano, hundredth, thousandth, millionth, billionth. And how many zeros are in a billion? 9. How many zeros do you need to move past the decimal to get to a billionth? 9. So 10 to the negative 9. 50 centimeters in meters. If you don't know by now, you're in sorry shape. Again, I'm still stuck with writing both of those with 3 sig figs. And I guess if you need it written out again, there's Coulomb's constant. Cancellation of units. Cancellation of units. And you see that we are going to be left with newtons per coulomb, which is reasonable. 9 times 10 to the 9th times negative 15 times 10 to the negative 9. I did not put those in parentheses despite my own good advice, so I'm just going to call it there. Divided by 0.5 squared. And we get negative 540 newtons per coulomb. All right. So that means if we put a negative charge nearby, we will get a positive amount of newtons, which will be repulsive. If we put a positive charge nearby, we would get a negative amount of newtons, which would be attractive. So this allows us to figure this out. If we put 1 coulomb of negative charge at this position, it would experience 540 newtons of repulsion. If we put half of a negative coulomb there, be 270, right? Newtons of repulsion. So similar to how you know that every kilogram at the surface of the Earth gets 9.81 newtons of force acting on it, this is a predictor at a certain radius, separation, distance, whatever you want to call it. But what if we had that metal sphere with charge built up on it, and instead of being 50 centimeters from the outside, let's say that it has a 50 centimeter radius, and we're talking about the inside. Ooh. Well, if you put a negative right here, and this whole thing is negative, it gets repelled, but it's also getting repelled here. So like if you tried to repel it toward this side, it just gets repelled back. What's the field potential there? Kick that question around in your head. The net force there would have to be zero, right? If the force is zero, then the field potential should be zero, right? If you let go of it, it wouldn't accelerate. So it would at least have no potential energy there. Ooh, let's start thinking about potential energy due to this stuff. Similar to gravity, right? Like you roll something uphill on your Sisyphean effort, you have invested this thing with some potential energy that it could use to roll back down the hill. So here we say it has potential energy due to gravity. Why? Sisyphus dragged this bad boy all the way up here and then it rolls down the hill. His work to move it upward, his work to make its weight go up a height, the force times the distance, and they're parallel, becomes the potential energy due to gravity. We are familiar with this stuff. This is classic. Everyone loved this last year, eventually. But then, if you were to take a negative and try to push it toward another negative, you are pushing it forward against the electric force through a distance. Work is force times distance as long as they're parallel. These two lines look parallel enough for me. So your work must be somehow preserved. Energy is conserved. Well, if you push it all the way to here so that they're almost smooching and you let go of it, what does it do? It shoots that way. Just like two magnets. Or as soon as you let go of Sisyphus's boulder, it shoots down the hill. Well, there it is. There's your potential energy, the work that you do to move it against the electric field's desired effect is stored as an increase in potential energy. If it moves along with the field in the spontaneous direction, as opposed to you having to do outside work on it, as it moves with the field spontaneously, it must be turning that potential energy into kinetic. There is some notation here that is worth noting. The electric field is always drawn around an object as it would affect a positive particle. So the test charge that you drop in near this positive would be repelled away if you dropped it right here. It would pew. If you dropped it right here, it would repel. If you dropped it right here, it would repel. Same here, same here, same here, same here, same here, same here. Notice that those radiating arrows have more space between them as you get farther away from the object. Similarly, the electric field would drop in magnitude the electric field potential would drop as you get farther away. So when you are looking at these, the direction of the arrows in a electric field diagram, the direction of the arrows indicates the um, direction a positive test charge would go, and the separation is indicative of the magnitude of electric field potential at that position. So here must have a lower electric field potential than here. And then as that positive charge moved such that it had lower field potential, its potential energy must be dropping as it turns into kinetic. If we took a positive here and forced it toward this, it is working from a point of low field potential to high potential, and the potential energy is therefore going up. From what? The work you put in is being saved. And as soon as you let go of it, that bad boy is going to follow those lines, shooting out into the distance. If we have a negative charge and we dropped a positive charge near it, it should be attracted and fall straight down toward it. Everything else that I said is still true, though. Here, the electric field potential is relatively weak. Here, it is going to, well, let's see. It is going to a higher potential. Does that mean that you are gaining potential energy? Nah, there's a negative sign there. You're losing potential energy. See? Sometimes those signs matter, kids. But that negative sign means that you're actually decreasing. It's becoming more negative, so decreasing in amount. Or the simpler way to think about it is it's moving with the field. That's like rolling downhill. You are losing potential and you are gaining kinetic. You could very easily get lost thinking about stuff like it is increasingly negative as the other thing becomes positive and you're trying to balance it out, but perhaps just the visual thing of it going downhill with the arrows is enough. But those arrows are drawn as they would apply to a positive charge. Everything reverses if you plug in a negative test charge. So a positive test charge moving with the lines of the diagram. And this is the electric field, so those lines represent potential paths of acceleration due to that electric force, or what Mr. Diaz, the old physics teacher, used to call electric field lines. He had that patois, right? So he had this really good joke he'd tell the kids. What does an electric field line do? Kids say, I don't know. What does an electric field line do? Meow. Get it? Electric field line? But a positive test charge moving along the electric field lines loses potential electric energy, UE, U for potential energy, little e for electric, and gains kinetic energy. So a negative test charge moving with the electric field lines, like a negative moving closer to a negative, well, it'd be like rolling uphill. It's going against a force, so you'd be gaining potential energy from the work you're putting in, losing kinetic energy because obviously this would be a retarding force because it's repulsive while you are trying to get closer. So a negative test charge moving with the electric field lines gains potential, loses kinetic. Positive going with the field lines loses potential and gains kinetic. And the contrapositives of both of those are still true using our good mathematical logic. If we switch positive to negative and with to against, a negative test charge moving against the field lines would lose potential energy and gain kinetic. So a -1 moving against these, well, here it should be attracted, right? So it would naturally want to go against these lines. So it would lose the potential as it speeds up on the way down. A positive test charge, and we're thinking of the contrapositive here. We swap negative for positive and with for against. A positive test charge moving against the electric field lines gains potential energy and loses kinetic. So if you add a positive charge right here, and it is moving against the field lines, as you force it forward, it is gaining potential from the work you are doing to push it against this repulsive retarding force. And as soon as you let go of it, then it moves with and gets that back. Hopefully some of that made sense. For a worthwhile exercise, draw the electric field around these two particles. And then when you're done with that, draw the electric field around these two particles. It's very easy to do. If you put a positive charge here, and they're always drawn as they affect a positive charge, it should shoot straight across. It goes from being repelled here to attracted here. It's going to be a nice, easy path to follow. Here, it would be pushed away, and then it would begin to be pulled down, so it would give you kind of a parabolic trajectory here. And of course, just flipping it over on the other side still works. So here, be pushed away, and eventually round out to being pulled toward if we zoomed in. Okay, that was easy. Do the same thing for the two negatives. Well, if you put one right here, it would be pushed, and then the other one would also push it away. So it'd be pushed away from both. Here, a little bit lower, same thing happens. And if you put it right there, perfectly smack dab in the middle, you'd end up with one of those no field potential situations where it's stuck. Everything's acting on it the exact same magnitude from multiple sides, and it's like a tug of war where no one's winning. So if you get asked anything about electric field potential or potential energy in an electric field, it is totally worth it, as always, to sketch out the situation, but there is already a convention and notation for those sketches. It's very easy to draw like a little stick figure of Galileo dropping weights off the Tower of Pisa, but when I'm talking about an electron being shoved near a nucleus, that is more abstract. Luckily, there's already a notation for those doodles to help you with those problems. I feel like we need to do another math practice before we call this one a day. Button it back up after surgery. So here we have a situation. A stationary block is charged with +6 times 10 to the -8 coulombs. Now that's pretty close to the -9 for nanocoulombs. So another way of writing this would have been 0.6 nanocoulombs. No, 60 nanocoulombs. Be careful about the way you're moving your decimals, kids. Let that be a cautionary tale. A zero point 0.8 kilo cart with a charge of 4 times 10 to the negative 8, or 40 nanocoulombs, is initially at rest on a frictionless track, and there's a distance of 1 meter between the two. There's no particular question to this. I just think we should figure out as much of everything about this as we can. There's all sorts of physical quantities that we could do. We could even, if you wanted, find like some kinematics. But as it moved away, the force would decrease in magnitude, inverse square law, right? So as the force drops, your acceleration should also drop. So this would be a case where there is negative jerk, but positive acceleration, in that it is speeding up, but it is speeding up at a lower rate. Kind of what's happening with inflation right now. The rate at which price increases increase is decreasing. Gotta love derivatives, right? Anywho, we have charge 1, the block. Charge 2, the cart. And the distance. Well, let's figure out, for one, the electric field potential at that distance from the block. So the electric field potential at 1 meter from the block. 9 times 10 to the 9 times 6 times 10 to the 8 divided by 1 meter squared. -8, +9, 6 times 9 is 54, times 10 to the first power would be 540, divided by 1 squared, which is 1, so this should be 500. I'm sorry, I got distracted by my computer making a noise. 540. Let's double check on that, though. 9 times 10 to the 9 times 6 times 10 to the -8 divided by 1 squared. 540. Okay, mental math is not necessarily superpower. So 540 newtons per coulomb is the electric field potential at the 1 meter distance. All right. Then if we take the electric field potential, 540 newtons per coulomb, and multiply that by the cart's amount of coulombs, we should get the cart's amount of newtons. And now we have the electric force on the cart. So 540 times 4 times 10 to the -8, 2.16 times 10 to the -5 newtons. All right. Feel like we're getting somewhere. With the force and the mass of the cart, we should be able to find the acceleration of the cart, at least at the beginning. Of course, as soon as it starts moving, there will be negative jerk because the force begins to get smaller, and the acceleration should therefore get smaller. But we can at least find the starting acceleration as it begins to roll. Just divide by the mass of the cart, which is 0.8. 2.7 times 10 to the -5 meters per square second, or 0.00027 meters per second, if you prefer to not have that in scientific notation, which would be 1, 2, 3, 4, 5, 6, 27 micrometers per square second. I don't know about you, but I'm thankful for the metric system. Good old Coulomb. What else could we potentially figure out about this? Well, these are going to repel. So if it starts to move spontaneously, then it must have had potential energy. Anytime you just let go of a situation and it starts moving and grooving, then you know that there is potential energy turning into kinetic because, well, things don't just suddenly start moving for no reason. That's second law of thermodynamics, even though we're now talking about electrostatics, but the same ideas do still apply. That kinetic energy has to come from somewhere. I guess that's the first law of thermodynamics. Damn, we can't get away from it. So we should be able to figure out how much electric potential energy it's got. Work is force times distance. Agreed? Only agree if they're parallel. Otherwise, you've got to use the cosine thing. But if that track was flat and we roll it right up to that guy, as we roll this card up, our work is being stored as potential energy due to electric force. So it should be electric force times distance. All right, let's try it. 2.16 times 10 to the negative 5 newtons. 1 meter away. Spend 45 minutes on your calculator, and you should get 2.16 times 10 to the negative 5 joules of potential energy to turn into kinetic. So I think that we should end our day with one last equation so that we can confidently state this for every other time we need to find electrical potential energy. Since this is true, U electric should just be KQ1 Q2 distance squared times distance. So it should just be KQ1 Q2 divided by distance once. And there we would get the amount of joules of electrical potential energy. All right, team. There should be a practice sheet for you to master these skills further. We'll also get to be doing fewer than 4 gizmos at a time now, so that might be a relief for some of you. Get to it. I don't even see what you're waiting for. Go out there, tell somebody about how great Charles Coulomb was, and do your gizmos. Adios, children.